Okay, here we have another stoichiometry example. And in this case, we have silver ions and chloride ions coming together to make a precipitate silver chloride, which is a solid. The delta H for this is negative 65.5 kilojoules per mole of silver chloride. So we're going to pay close attention to what the enthalpy refers to. In the last example, it was the reactant in video B. In this example, it's the product, silver chloride. So we're going to be able to use our enthalpy as a conversion factor. Okay, so we have 3 different questions here within videoC. For this reaction, calculate delta H for the formation of 0.200 millimoles of silver chloride. Well, we know that 1,000 millimoles equal 1 mole. Okay, so we know that the delta H for the formation of 1 mole of silver chloride is negative 65.5 kilojoules. So we want to know what is delta H for a different number of moles, in this case 0.2 millimoles. So for question A, I'm going to start out with negative 65.5 kilojoules per mole. Now, because throughout A, I'm just going to be dealing with the silver chloride, I'm not going to write the word or the symbol for silver chloride here. Then I know that 1 mole is equivalent to 1,000 millimoles. And in this case, if I stopped here, I would know how many kilojoules per 1 millimole. But I don't have 1 millimole, I have 0.2 millimoles. So as you can see, we are going back to doing a lot of dimensional analysis as well as stoichiometry. So if those things are rusty, you might want to go back to the material we did in the fall. We did all of those dimensional analysis workshops, and chapter 4 included stoichiometry. So that's where you would go to refresh your memory. Okay, so the answer here is negative 0.0131 kilojoules, and that has 3 significant figures, 1, 2, 3. So that is the answer for part A. For part B, we are asked delta H for the formation of 2.5 micrograms of silver chloride. Okay, so now we're looking at mass. So that means we're probably going to need the molar mass for silver chloride, and that is 143.32. You would get that from the periodic table. So for part B, again, I'm going to start with the amount of heat that's required to make 1 mole of silver chloride, and then I'm going to figure out how much heat is required for 250 micrograms. The other thing I'm going to need to know is the fact that 10 to the 6 micrograms is 1 gram. That's another thing you might want to review, are your metric prefixes. Okay, so I need to get to micrograms, so I'm going to go ahead and go from 1 mole to 143.32 grams. Silver chloride. Okay, so now I know how many kilojoules per gram of silver chloride, but I'm interested in micrograms. So I'm going to convert to micrograms and then multiply by 2.50 micrograms. That gives me 1.14 times 10 to the minus 6 kilojoules. And we're not asked for a particular unit for joules. So I've left it in kilojoules, but you could also convert it to joules because this 10 to the minus 6 is kind of an awkward number. So you could convert it to joules if you wish, or millijoules, which would be 1.14 millijoules. So this is a negative number in both cases. Okay, part C. Part C says delta H for the dissolution of 0.150 nanomoles of silver chloride in water. Okay, so this seems a little confusing. Why are we talking about dissolution of silver chloride? Well, if we go back to our balanced chemical equation, we see that the solid is on the right and the ions are on the left. The dissolution of the solid would be the reverse direction. So the reverse reaction is silver chloride solid making chloride ions and silver ions. That is the dissolution, or the dissolving of the silver chloride into its component ions. And so the delta H for that is positive 65.5 kilojoules per 1 mole. So the key in part C is just to know that you have to change the sign from negative to positive because you're changing the reaction direction. Okay, so for part C, we're starting with 65.5, which is positive, kilojoules per mole of silver chloride, and then we are asked for the dissolution of a certain number of nanomoles. So we have to go from moles to nanomoles, 10 to the 9th nanomoles. And then the number of nanomoles in the question is 0.150 nanomoles. And that gives us 9.82 times 10 to the minus 9 nanomoles. And again, and that's positive. That has 3 significant figures. The answer to part B also had 3 significant figures. So this question requires that you remember a lot. You remember your stoichiometry, your metric conversions, and how to do dimensional analysis.